Any questions from Thursday's discussion? What causes an NMR signal to be split? Yeah, adjacent protons affect the effective magnetic field that nucleus that's undergoing resonance is seeing. So spin, splitting distance. Equivalent protons do not split each other. So when you go to apply the N plus rule, it's kind of like how do I count all the protons? We'll look at some examples. So you don't count the other equivalent protons. Protons bonded to the same carbon will split each other if they are non-equivalent. We're going to spend some time on that. Protons on adjacent carbons normally will split each other. Protons separated by 4 or more bonds typically do not split each other. So this proton here will split that one and vice versa. And if I count bonds, 1 bond, 2 bond, 3 bonds, so there's where we're gonna observe spin splitting. When the hydrogen atoms are 4 bonds or more apart, spin splitting is not normally observed. When we actually see it, we call it long-range coupling. I don't think we'll really get into that. So what you want to be able to do is recognize groups. Our alkyl groups, methyl, ethyl, isopropyl, those 3 would serve you very well. And looking here, how many signals do I see? Remember, this is TMF. Excuse me, TMS, trimethylsilane. So I see 1, 2, 3. And when I look at this molecule, we're going to count all these as being about the same. So a signal from the hydrogens on the benzene ring. And here's this ethyl group. And let me just put one of those carbons there and count 1, 2, 3, 4. So the point being, these hydrogens are not going to be split by those. It's 4 carbons away. So let's review the N+1 rule a little bit. These hydrogens are split by 1, 2, 3. So N+1 is going to be 3 plus 1 is 4. And what do I see here? Let me blow that up a little bit. We see a quartet. And what do I see here? Well, these signal from these 3. We go N is 2, and so right here we see this thing, call it triplet. So I tell students up here right above 7, that's where you see hydrogens on a benzene ring, and for the most part, we don't try and make a lot of sense out of it. Now what we can make sense out of is this integration. That integrates to 5, 2, and 1. And notice 5 protons, excuse me, did I say 1? 5, 2, and 3. 5, 2, and 3. So we get the number of protons giving the signal. So here's how we apply the N+1 rule. Questions? So whenever I see a triplet and a quartet, I'm kind of thinking ethyl group. So here is the isopropyl group. Maybe the first thing we want to do is look at this and say, how many signals would I see? These are equivalent, so 1 signal there, 2 signals, 3. So here's the TMF, and I have 1, 2, and 3. Makes sense? Now once again, these protons here, if I count bonds away, 1, 2, 3, 1, 2, 3, 4. These protons don't get split by anything. So when I apply N+1, I go 0 plus 1 to get a singlet. And that's this thing right here, single peak. Now over here, I have a 1. So this thing's going to be a doublet. There is the doublet caused by the signal from these protons. And notice those are the furthest upfield, the most highly shielded. So here's the interesting thing. 4 bonds away from these hydrogens, not going to be split by these hydrogens, but we can count 1, 2, 3. So when I apply the n+1 rule here, 3 and 3 is 6, that's 7. And I count 1, 2, 3, 4, 5, 6, 7. Luckily it's blown up so we can see that. And this is called a septetlet, or a septet, octets, quartets. Any questions? Right, how shielded they are, whether they're upfilled or downfilled. If on a quiz you put it in the wrong spot, you wouldn't get marked off. Yeah, the 1, 3, 6. Right, so this is the integration. This peak integrates to 1. This peak integrates to 3, that's the singlet. And this 6 here gives you these. So to answer Tianya's question, these here are both kind of de-shielded by this oxygen. I'm going to put them a little left. These look like something that's going to be the most shielded. So I'm going to put these over here on the right. And then whether I put this one here, this one here, or this one here, on your quiz, I wouldn't care. But it turns out that this one's more de-shielded than this because of these two more alkyl groups, and we call this the methine hydrogen. So we had methyl hydrogens on an alkane furthest that way, and then we had a methylene where there was 2, and then the methine, and as we went from methyl to methylene to methine, things became more de-shielded and went down-filled. So both these points make sense to us. The two methyl groups are equivalent. They give 1 signal. That's the doublet. 3 signals. Great stuff. Oh, my favorite thing, a little problem. And if you have the slides, you can figure it all out. But this is going to be really good for us. Propose a structure for the compound of molecular formula C4H10O, and here's the proton NMR spectrum. So when I look at this, first thing I do in my brain, I go 4 times 2 is 8. 1, 2, 3, 4. How many signals is this going to have? Just 2. These are equivalent. All right, and how many signals do we actually have? 1, 2, oh man, 3, 4. I suppose there's a couple other ethers we could have. 1, 2, 3, 4. Here we'd have a singlet. All right, this one we'd have a triplet and a quartet. But I'm seeing a doublet. I'm seeing a big mess, and I'm seeing a doublet there. And unfortunately, the integration's not being shown right now. Now look at this mess. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't know if I necessarily believe it. 1, 2, 3, 4. Before too long, I'm going to have every constitutional isomer up here that has that signal. How many signals would this have? This is going to have 2, 1, and 2. Now look, look at this thing. 1, 2, 3, 4. All right, so this is T-butyl alcohol, isobutyl alcohol, 1-butanol, 2-butanol, diethyl ether, methyl propyl ether. I might have everything I need. 1, 2, 3, 4. Thank you so much, Jonathan. 1, 2, 3. Yeah, don't screw up your number of signals. All right, so we can probably start ruling these out. How many do we have? 1, 2, 3, 4. So rule that one out, rule that one out, rule that one out. This weird business and some doublets. I got 2 doublets. So this methyl group here, they're equivalent. That's going to give me a signal split by this 1. So n+1 is going to give me a doublet. That could be this thing here. This mess, how many should I see? 3, 6, 7, 8 plus 1 make how many? 9. I'm gonna believe all those. What next? And this might be a little weird because alcohols are a little weird. We'll see in a slide or two. I'm pretty sure this one is it. 1, 2, 3, 4 signals. 1, 2, 3, 4. And we get, the only way we can get our 9 peaks here is to have this thing split by 3, 6, 8. That would give rise to that thing. This thing here, if we count that one and count that one, we should see a triplet. I'm not seeing a triplet, but a lot of times this thing comes off because it's acidic. It's a little weird. So this thing should give us a triplet there, split by those 2. Alcohol's a little weird. You don't always see that, so I think this single peak is that. And I think this thing is split by 2, and that's this one here. And those slides up on Moodle, they work through that example. Coupling constants. What is a coupling constant? The coupling constant is the distance between the peaks of a multiplet. Given in Hertz, coupling constants are independent of strength of the magnet. Multiplets with the same coupling constants may come from adjacent groups of protons that split each other. Well, I don't like that word may, and the whole reason we go through this is because that's the beauty of it. If you see a bunch of different peaks, how do you put together what is splitting what? So these are things you can look up, or when you go to solve a structure, you can have a table of coupling constants and your chemical shift values. So let's just say everything else is 4 carbons away, or 4 bonds. These 2 are going to split each other. In theory, we'd see doublets, but each doublet would be split by 7 Hertz. And it says that sigma bond can rotate. When these 2 things split each other, the peaks, the multiplet, whatever it is, will be split by 10. If they're in the trans position, 15. Geminal 2 Hertz. And some of you might be saying, well, aren't these equivalent? We're going to get into that. If this was the simple hydrocarbon ethene, we would see 1 peak and no splitting. But we're going to imagine the carbon chain continues, maybe in OH, whatever. Same thing with hydrogens on a benzene ring and allylic. The value of 7 Hertz in an alkyl group is average for rapid rotation about the carbon-carbon bond. If rotation is hindered by a ring or bulky group, other splitting constants may be observed. So I said most of the time when we see signals up above 7, we just say, oh, that's benzene ring. And at least I don't really try and figure out what's going on other than it integrates to the correct number of hydrogens, and I don't look for any splitting things to tell me anything. This compound here, we see it nicely. If I said, how many signals should we see? That's the first question to ask when you look at trying to fit a compound with a spectrum. Or if you look at a spectrum, how many signals? Remember, this is TMS, so I'm seeing 1, 2, 3. That means we have 3 types of hydrogens. So there's the methyl group, there's these 2. Notice there's a line of symmetry there. So these aren't very much alike because these are closer to the methyl group and far away from this electronegative nitro group. So we say these are equivalent, these are equivalent. So here's 1 signal. This is the furthest downfield, the most de-shielded. Of course, this is the most shielded. And notice we get a singlet. That's because we counted 1 bond, 2 bonds, 3 bonds, 4 bonds. These hydrogens are too far away to split those hydrogens. There's the singlet. So these are split by 1, N is 1. 1 plus 1 is 2. So we see a doublet. And this doublet has a coupling constant of 8. And this one over here has a coupling constant of 8. So we say they're splitting each other. Para-nitrotoluene has 2 pairs of equivalent aromatic protons, A and B. Since the coupling constant for the ortho here, is approximately 8 hertz, and the peaks of the signal will be separated around 8 hertz. Whoops. Here is what we call ortho. Here's what we call meta. We'll see this more in the benzene chapter. So when we see that, we know how far apart the hydrogens might be on the ring. Vinylic coupling constants. So here is a compound. How many signals should I see? Here's a hydrogen, here's a hydrogen, hydrogens, hydrogens, hydrogens. I'm thinking 1, 2, 3, 4, 5. Let's see. 1, 2, 3, 4, 5. All makes sense there. Notice here, 1 bond, 2 bond, 3 bonds, 4 bonds. This is the singlet. And what's giving me the 2 triplets? Well, here's 2 protons. Here's 2 protons. These 2 protons, they only see those 2. N equals 2 plus 1 is 3. So this should give me a triplet. This should give me a triplet. I'd imagine this triplet is further downfield, de-shielded by this pi bond and electronegative oxygen than this one here. All right, so here's our singlet, this one, and then here we got these 2 vinyl or vinylic hydrogens. And this one right here, if I count number of bonds, if I go this way, I'm probably going to get to 5. 1, 2, 3, whoops. 1, 2, 3, 4, I guess. So the only thing that can split this proton is this other one. The only thing that can split this proton is that other one. So if I was going to label these, that's those protons. I couldn't keep my alphabetation going. I went alphabetically around here, but this one is more de-shielded, ends up down there. The coupling constant for the cis coupling is approximately 10 hertz. So the peaks should be separated by approximately 10 hertz. That's enough for today.